Okay, and this will be the last part of our synthesis methods for nanoparticles, one-dimensional, two-dimensional nanomaterials. In this section, we're going to cover mostly the 1D, 2D nanomaterials, where we will learn the techniques or focus more on the techniques to make thin films and nanowires. So in general, the production route for one-dimensional rod-like nanomaterials by liquid phase methods is similar to that for the production of nanoparticles that we learned in part 2, which involve the self-assembly methods that use the highly anisotropic bonding nature of asymmetric molecules to cause them to self-assemble into tubes rather than spheres, forming cylindrical micelles in this case. And the amphiphilic molecules, which you all should know what they mean by now, are then removed with an appropriate solvent or by calcining to obtain individual nanowires. So this was an example to obtain the 1D materials by liquid phase synthesis method. And other than that, we will look at some ways to make things like thin films. And why do we care about that? Like as Bilge Hoca explained it pretty well, shape control, morphology control, particle size control is very, very important for controlling the mechanical, electrical, magnetic, optic properties of what we're trying to do in real life. And another example can be given as shape-controlled catalysis, which after our class, Deniz Üner will give you more detailed examples on this fact. But changing the morphology of nanocrystals or the shape make a big deal in the world of catalysis, for example. Okay. So we're going to go over shortly and surely on the techniques to make 2D materials, okay? And one way to do that is electrodeposition. It is a very well-known technique, and the common idea is that the ions in solution sometimes replenish from an anode, and in this case here is my anode, okay, and the ions are replenished from an anode, are deposited onto the negatively charged cathode, carrying charge at a rate that's measured as a current in the external circuit. Okay, electrodeposition is a very highly used technique. The process is relatively cheap, fast, and allows complex shapes. And then the deposit can be detached if the substrate is chosen to be soluble by dissolving it away. So there are ways to obtain what you made at the end of your electrodeposition technique. And the challenge, of course, as always, is to control the structure. And in this case, to make nanoparticles or layers, it's necessary to stop each crystal's growth while it's still tiny and to nucleate more. And there are a combination of tricks that you can do during electrodeposition, which pulsing the voltage causes little bursts of crystal growth, adding growth inhibitors, or you make a combination of different techniques with a high current density. For example, nucleate many crystals but allow little time for each to grow, giving a nanostructured deposit. Okay, so this is a very well-known technique. Another technique is called physical vapor deposition. This is very similar to what we learned in part 2 for making nanoparticles, where we were using in that case the cold finger to obtain the nanoparticles that we create. Unlike that, in PVD, a thin layer of a material, usually a metal, is deposited from a vapor onto the object to be coated. So this is my object to be coated, and this is where the vaporization is happening. Okay, and the heater, the evaporant, and the evaporated atoms goes and sticks onto the substrate and collected as a deposit. So the vapor is created in a vacuum chamber by direct heating or electron beam heating of the metal. Okay, here the choice of metal is important, from which it condenses onto the cold substrate. Okay, so this is very much similar to what we learned before, but in this case we have a 2D thin film, much like steam from a hot bath condensing on a bathroom mirror. It's very similar to that, as you can imagine. In PVD plating, there is no potential difference between bath and workpiece, and so on. So in PVD sputtering, argon ions are accelerated by the electric field onto a metal target. By introducing reactive gas, compounds can be formed. Okay, so you can use these reactive gases if you want. Sputtering titanium, for example, in an atmosphere of nitrogen, for instance, gives you a coating of titanium nitrate sort of things. So what's important here to keep in mind is material evaporated by heating, by ion bombardment, by laser ablation is deposited on a substrate target. The deposited layer can be of nano thickness. Okay, so all the things that you had learned with Bilge Hoca and all the tricks with the electrical conductivity and things like that, the thickness and so on, these are the methods to be able to obtain those kinds of materials in real life. You can think of that like a nanoparticle of carbon could be formed by burning wax. Wax, which is made up of long chain molecules of carbon and hydrogen, decomposes and loses hydrogen atoms. The carbon atoms may then condense to form particles of carbon, and there you have your carbon in nanosize range, for example. Similarly, complex organic compounds that contain atoms of interest may be decomposed, and the fragments may condense to form nanoparticles that we desire. Okay, so there are like 3 steps here. You have to pick your material of interest, where it's heated and decomposed and broken into its fragments, and then you condense it and then you collect it. Such a starting compound is called a precursor. Precursor, you have to know this word very well. It's very important to choose the right precursor for the nanomaterial that you desire. An example of a precursor is, for example, this compound here. On heating this, it decomposes to form alumina, for example. Okay, so this is my precursor, the 3-butoxyaluminum in this case. Depending on the source of energy, these processes may be classified as chemical vapor condensation, microwave plasma processing, combustion flame synthesis. They all sound very complex names, but the only thing that's changing really is the energy that you are supplying, the type of the energy that you're supplying to evaporate your material to form whatever decomposed parts you want to obtain. Okay, so for example, chemical vapor condensation. Okay, this is another very well-known, very popular technique. And in this technique, look at my precursor. Unlike the other one here, I was evaporating it. Here I have a gaseous precursor of 1, 2, 3, whatever you want to make it, change the number of precursors you're using. The precursor vapor is passed through a hot vault reactor, and this is my reactor. It's heated. Okay, while it's passing here, it decomposes into these little nanoparticles. The nanoparticles are carried by the gas stream and collected on my cold finger. Okay, these, as you see, now you're getting into obtaining these nanoparticles to make like quantum dot 0D, 1D, 2D materials. They all have some similarities which you should keep in mind. Okay, the nanoparticles are carried and collected on the cold finger. We said that the size of the nanoparticles is determined by the particle residence time, so how much time it's spending in your reactor, for example, the temperature, the precursor composition, the pressure. These things are very important. You have to pick a method where you have control over what you are making, the size of the nanoparticles here, the morphology, okay, whichever method is giving you the most amount of control for whatever application you're going to use it for, you have to go ahead and use that technique. Or, like I said, if you don't want to like use these precursors heated in a furnace or whatever, but you have, let's say, for some reason, microwave plasma. And in this case here, a microwave plasma is used to provide the energy required to decompose the precursor, okay? That's why the name changes into the microwave plasma processing. The size of the nanoparticles in that case is determined by the precursor composition, of course, pressure, particle residence time. Because thermal energy is not being used in this case, the reaction can be carried out at a much lower temperature. This is important. It can be important for you because lower temperature means it reduces the tendency of particles to agglomerate, or in some cases it doesn't allow the nanoparticle to grow higher than a certain size because it doesn't have that temperature. Okay, so you can have a control, more control over what you're making if you have like a microwave plasma process. Or combustion flame synthesis, and in this case I don't have the microwave, I don't have my microwave, or I don't have my what is it called, the precursors, the heating or whatever. I have literally flame. Okay, so energy to decompose the precursor in this case may be supplied by burning, literally burning a fuel air mixture with the precursor in order to reduce agglomeration. The flame is specially designed to be low pressure because flame, as you know, it's got all sorts of temperatures which change the color of your flame, right? If you light a flame, you will see different color ranges, which means that it has different temperature profiles. But such a variation in the temperature profile of the flame would cause nanoparticles of different sizes to grow. So you really want to have a control over the temperature to obtain a flat temperature profile that is a constant temperature across its width. Okay, in this process, the appropriate, again, you have the precursor, vapor gas is mixed with a fuel. The mixture is burned through a specifically designed burner. So in this case, I have a burner, not a microwave, not a, you know, like not like something like an oven, but a flame. And again, the nanoparticles may be collected on the cold surface. Okay, these are all bottom-up approaches, and now I think you're getting used to the way to make things happen in the nano world. By proper choice of the precursor, again, the different nanomaterials can be synthesized. Some processes are better than others. For example, pure metals are almost always made only by gas condensation if you want to make pure metals in order to prevent contamination. In addition, some methods are limited in the kind of nanomaterials they can produce. For example, combustion flame synthesis is limited to the production of oxides because you're burning it, as any particles formed in the flame always end up getting oxidized. Okay, so let's continue with another very well-known technique. It's called the chemical vapor deposition. Okay, it's called the CVD. So instead of my, where's the PVD, where I was heating is vaporizing it, collected on a cold surface. Now things are getting chemical. Vapor deposition. What happens in a CVD process? It's now probably the most common of all bottom-up approaches. It's used today to grow structures like nanotubes, nanowires, nanoparticles, aided by several different types of chambers, growth enhancing methods, and this process consists of decomposing a gaseous precursor that adheres and accumulates onto a substrate. It's usually the silicon wafer or quartz slide. And you need a catalyst. So this technique requires a reaction. Okay, this is important. It goes through a reaction, and the reaction product is collected on your substrate. So this is like A plus B going to C. You are making this happen in your reactor. A catalyst is normally deposited or patterned on the surface of the substrate and is used to activate the chemical reaction between the substrate surface and the gaseous precursor. Okay, so you have to know really the difference between a CVD and a PVD in its very major form. Okay. Basic CVD is a process where thin films are deposited on a substrate. This is a very highly used technique. This is done by chemically reacting various gaseous or volatile compounds on top of my substrate. Then the product from the reaction attaches itself to the substrate to form a thin film from a few atomic layers thick to microns thick, which you can control. Many chemical vapor deposition reactions occur at elevated temperatures in a range of 900 to 2000 degrees C. Okay. And there are a few different types of chemical vapor deposits. This is a very common route to make carbon nanotubes. If we have time, we're going to go over that, the production of carbon nanotubes as well. The first one is laser-assisted CVD, arc chemical vapor deposition, thermal chemical vapor deposition. All of them are very highly used, especially these two, I think, are used in industry because it gives you a high yield of the material that you're making, which is usually hard to obtain. Okay, and for example, if you are using the thermal thing here, thermal chemical vapor deposition, as you see, I have a mixture of ethane and the argon is carried, and here I have a furnace because it's the thermal thing, so I have a furnace, I have a bare substrate here. Okay, and so what's going on? Thermal CVD works by reacting two or more gases above a substrate to form a thin film. And don't forget, you can have catalysts here on your substrate, catalysts which pushes this reaction to occur in a certain way, okay, for you to be able to obtain, for example, single wall nanotubes or multi-wall nanotubes. Okay, the type of the catalyst you're using, the type of the CVD technique you're using makes a big effect on the type of nanotube you are obtaining, for example, in this case. The reactive gases are fed into the chamber through the gas inlet valve. The reactive gas travels down the chamber while its temperature increases, and then when the reactive gas hits a certain temperature, which happens here, the reaction takes place, forming a product. And the product, okay, so I have a reaction here, okay, I have a reaction here, and this is my, let's say my product is P. The product is deposited on the surface of the substrate because this is where the reaction is happening, okay, and the byproducts leave the system through the gas outlet. And this can be as simple as you see in this picture here, okay? It's a simple tube furnace, and this is where you're making all your synthesis, for example, in a lab. And I have the thermal CVD can be used to deposit, for example, silicon dioxide film on a substrate. Okay, you can use these, and in this case, these are my precursors. Are the reactive gases used. These gases are heated up until the reaction occurs. This reaction takes these precursors and form my product, and chlorine gas, the silicon dioxide deposits on the substrate. Or if you are interested in formation of like some sort of carbon nanotubes, you can use methane as a precursor. This will be my reaction product depending on the catalyst. This can be single wall or multi-wall nanotube, okay? The catalyst for the reaction can be provided on the substrate or on the gas mixture. The reactor design can change. It may have a huge impact on the product quality of your nano particle or nano like 2D material you're obtaining in this case. But the main benefit of a tubular reactor, which we have here, is that it's relatively easy to model the flow of the gas through the reactor, and it allows for a more even temperature distribution, which affects what? You answer. Which affects, for example, the particle size distribution or the morphology, because different temperature can create different types of products. Okay, so you really have to have a total control over what you're making in your process. Or, for example, people have come up with things like, okay, I don't want to put substrate like this, but I want to give it some sort of an angle so that the thickness can be controlled in an enhanced way. So, for example, in this reactor, the substrate at an angle is at an angle to the incoming flow. This is to get a more even boundary layer across the substrate, and the boundary layer can be thought of as a layer of gas that's not moving, and it can affect what you're obtaining at the end of your reaction. Okay, the thinner boundary layer will yield a thicker film, for example, and so on, which, as you know from Bilge Hoca's class, the thickness can have a huge impact on the application results that you are aiming for. Or you can not only obtain 2D materials, but you can obtain like particle synthesis using CVD. And CVD can also produce small particles along with thin films. These particles can range from a few nanometers to few microns. These particles are formed in the gas of the reactor and can be collected on the surface of the reactor or can be collected from the gas outlet of the reactor. The only difference is the temperature range used through the reactor. Different temperature gradients will produce different forms of product, which we already had gone through many times. And this, I think, is more like a summary. The particle chemical vapor deposition works like thermal chemical vapor deposition. So what was it? Let's go through it again. The reactive gases are fed to the reactor through the gas inlet. The reactants are heated up until the reaction occurs. At this point, the solid product will come out of the gas phase and collect on itself. This is called homogeneous nucleation, which we will go through in our next class. Once the solid is produced from the gas phase, it's cooled. As it continues down the chamber, as it cools, it slowly collects on itself, forming small particles. Okay. Sometimes a nozzle reactor is used. A nozzle reactor is something like that. You have the cold tube here. It's similar to the tube reactor. However, there is a cold rod which goes up to the center of the tube. This cold rod cools the gas, which allows the particles to come out of the gas phase. So you see, it's the combination of all the things that we had heard about until now. Okay, you use not that, but maybe a cold tube, and then it changes the name of the process. It all depends on what you want to obtain. Do you want to make like quantum dots, or like nanowires, or like thin films? You pick your method accordingly. Okay, the temperature profile is important. That's what we had already talked about. Any variation in the temperature will lead to different sized particles. If particles are being produced, if the temperature is similar, the particles will have a narrower size distribution, which, as nanotechnology people, is an important factor for us. Okay, and these are my references, and this is it, people, for different types of synthesis methods. We had gone through 0D, 1D, 2D material synthesis in liquid phase, in gas phase, and our next class will involve homogeneous and heterogeneous nucleation details. So